Swayam Prabha. Digital India. Educated India.
Hello, I welcome you all in the course on refrigeration and air conditioning. Today we shall be covering the introduction to refrigeration. What is refrigeration? As per the definition of refrigeration, it is a process of maintaining temperature of confined space lower than the surroundings. So if we are able to maintain, for example, if we are able to maintain the temperature of this room less than the surrounding temperature, the refrigeration process has been carried out. Now how it is different from cooling? Now cooling is a process in which the heat transfer takes place from higher temperature to lower temperature. I will give you an example. Suppose you have a coffee mug placed on a dining table. Temperature of the coffee is 80 degrees centigrade, surrounding temperature is, let us say, 30 degrees centigrade. The heat transmission will take place from coffee to the surroundings, but this process is not refrigeration process. Refrigeration process will come into the picture when you are maintaining the temperature of the coffee lower than 30 degrees centigrade by extracting heat from the coffee and pumping it to the surroundings. The unit of refrigeration, the refrigeration process or refrigeration equipments, they have a unique unit which is known as tons of refrigeration. Now regarding the tons of refrigeration, there are two types of tons. One is TON and another is TONE. And I have found that students are often confused about these two tons, TON and TONNE. This TONNE is a metric ton and it is 1000 kgs. Now this ton has two values. One is imperial ton or UK ton, which is 1016 kgs, and this ton is 2000 pounds, and this 2000 pounds will come around 907.2 kgs. So there is a wide difference between imperial ton or British ton and the US ton. Now tons of refrigeration. Which ton is used for defining the refrigeration effect, and this ton is used for defining the refrigeration effect. Now 1 ton of refrigeration means if we are able to produce 1 ton of ice within 24 hours from 32 Fahrenheit water available at 32 degree Fahrenheit, and this 32 degree Fahrenheit water is converted into 32 degree Fahrenheit ice. So 1 ton of refrigeration addresses the conversion of 2000 pounds of water into 2000 pounds of ice within 24 hours. The water is available at 32 degree Fahrenheit and the ice is also formed at 32 degree Fahrenheit, and this 32 degree Fahrenheit is equivalent to 0 degree centigrade. In SI unit it is 0 degree centigrade. So 1 ton of refrigeration is equivalent to 12,000 BTU per hour. Now there is another term which is introduced here is BTU. It is British thermal unit. It is equivalent to the amount of heat required to increase the temperature of water by 1 degree Fahrenheit. This British thermal unit, if we take equivalence of British thermal unit in kilocalorie, so 1 BTU is equal to 0.2522 kilocalorie. MKS system, the heat was expressed in terms of kilocalories and work was expressed in terms of joules and kilojoules. But in SI system nowadays, we follow SI system, they are expressed in terms of joules and kilojoules, or watts and kilowatts, that is heat transfer rate. So, 1 BTU in SI system, work and heat both are mutually convertible, that is why both are expressed in terms of joules or kilojoules, or heat transfer rate or work transfer by watts and kilowatts. So, 1 BTU, as I said, in MKS system it is 0.2522 kilocalories. In SI system 1 BTU is equivalent to 1055 joules, right. So, now if we have 12,000 BTU per hour, if we multiply this 12,000 multiplied by 1055 per hour divided by 3600, what you are going to get? The approximate value of 3.5 kilowatt. So, the heat transfer rate or heat extraction rate of 3.5 kilowatt is equivalent to 1 ton of cooling. Now, if you want to have, nowadays we do not use MKS system, but still if you want to have idea about the MKS system, in that case 1 ton of refrigeration is going to be equal to 12,000 BTU multiplied by 0.2522, that is kilocalorie per hour, that is 60 minutes. So, it will be come around, I will give you approximately 50 kilocalorie per minute. So, and it is also expressed in terms of kilojoules per minute also, it is exactly 211 kilojoules per minute. So, if you want to express per minute, in MKS system it is 50 kilocalories per minute, 211 kilojoules per minute, and nowadays we are accepting this as, because if you divide this by 60 you will be getting approximate value of 3.5 kilowatt. So, nowadays in SI system 1 ton of cooling is equivalent to 3.5 kilowatt of heat extraction. Now, we will go to the Carnot cycle for power generation, because any cycle, whether it is refrigeration cycle or power generating cycle, it is compared with its performance is always compared with the performance of Carnot cycle. So, Carnot cycle for power generation consists of 4 processes. If we expressed in PV diagram, there are 4 processes starting from adiabatic compression, state 1 to state 2, this is adiabatic compression, right. Then isothermal heat addition, isothermal heat addition from process 2 to process 3. Now, process 3 to process 4 again adiabatic and isentropic expansion, and then process 4 to process 1 constant temperature heat rejection. So, in the process 2 to 3 the heat is added, and process 4 to 1 heat is rejected. In these 2 processes, because they are isentropic process, reversible adiabatic processes, Q is 0, heat transfer is 0. Now, if we transform this Carnot cycle on temperature entropy diagram, this is TS diagram. Now, process 1 to 2 is constant entropy or reversible adiabatic process, this is process 1 to 2. Now, process 2 to 3 is constant temperature process, this is TH. Now, process 3 to 4 is again expansion process where we get the work output, and process 4 to 1 is again heat rejection process. So, here heat is added QH and here heat is rejected QL. Now, this is a imaginary cycle for power generation. And according to the second law of thermodynamics, no power generating cycle can have efficiency more than Carnot cycle, and that is for this reason this cycle becomes important for the comparison of different cycles for power generation. But how it is relevant in refrigeration, right? In refrigeration process, if you reverse this cycle, in that case, at lower temperature, heat will be added. Instead of removal of heat, the heat will be added to the cycle, the direction will change. Process 1 to 4. 4 to 3, again the direction will change. Instead of expansion, in reverse cycle, the compression of fluid will take place. And from 3 to 2, again, instead of heating, the cooling of fluid will take place. And instead of heat being added, heat will get rejected. And from 2 to 1, the expansion of the fluid will take place. So, we have another cycle which is reverse Carnot cycle, and in this cycle the net effect is transfer of heat from lower temperature to higher temperature. And this cycle can produce the refrigerating effect, right. There are certain drawbacks of Carnot cycle. In Carnot engine also there are certain drawbacks, right. We will not discuss all those drawbacks here, because we are not here using a Carnot engine, we are using reverse Carnot cycle, and this reverse Carnot cycle is often referred as a standard cycle for comparing the performance of different refrigeration cycles. Now, in this cycle, the heat is taken at the lower temperature and it is rejected at the higher temperature. Now, performance of this cycle. Normally, in engines, the performance is expressed by thermal efficiency. Now, efficiency of any instrument or any equipment is very important, whether it is a refrigeration cycle, refrigerator, or a compressor or an engine. So, as an engineer, we should have fairly good idea about the efficiencies of the system. For example, if I say I have a compressor which has efficiency of 70%, is it acceptable or not? The compressor is reciprocating compressor. Another case, I have an engine which has efficiency of 40%. Is it acceptable or not? Remember, in engines we are converting heat into the useful work. When we are converting heat into the useful work, in that course we are able to convert 35% of heat into the useful work. That is good efficiency. Normally in a normal engine, 1/3 of energy is converted into the useful work, 1/3 of energy goes with the exhaust, and 1/3 of energy goes with the cooling water, which is circulated in the jacket, water jacket around the covering the cylinder. So, for compressors, let us take example of compressor. If it is a reciprocating compressor, if I have 70 efficiency is 65% or 70%, this efficiency is a poor efficiency, because in a compressor we are converting, there is a work to work interaction, right. In work to work interaction we are losing 30% or 35%. So, the efficiency is low, and that too in reciprocating compressor. In if you take the axial flow compressor or the centrifugal compressor, the efficiencies are high. Even axial flow compressor, the efficiency can go up to 90%. But the 90% efficiency for a transformer is a poor efficiency, because in transformer again we are converting one form of electrical energy to another form of electrical energy, and in that course if we are losing 10%, that is also it's poor performance. Transformers have 99% of efficiencies. It can be up to 99, it is more than 99% of efficiency. So, efficiencies are important. So, as a practicing engineer, we should have fairly good ideas about the efficiencies of the system. Now, here in Carnot cycle, now the efficiency of a cooling system or refrigeration system is expressed by coefficient of performance. Now, coefficient of performance is here, it will be the cooling effect QL divided by the work spent for this cooling effect. Now, as you know, in a Carnot cycle, the work is equal to QH minus QL. We can draw from the principles of the first law of thermodynamics, cyclic integral of work is equal to cyclic integral of heat transfer. Now, let us try to find the value of QH and QL. If we are able to find the value of QH and QL, we can find the COP of the system. Now, in order to find heat transfer at higher temperature, let us take rectangle A23B. Now, this rectangle A23B, if we take area of this rectangle, it will be area A23B is equal to TH S3 minus S2. S3 is entropy at this place and S2 is entropy at this place. Now, area of A, this is 1, A1 4B will be the heat transfer from surroundings to the fluid. So, this area is TL S4 minus S1, and net work done in this process will be given by the area of this rectangle. So, the area of rectangle 1, 2, 3, 4 is equal to TH minus TL multiplied by S3 minus S2. Now, if you look at these two equations, in order to find COP of the cycle, it is heat transfer, that is QL, and QL is TL S4 minus S1 divided by area of this rectangle, which will give us the work spent in for this heat transfer, and that is TH minus TL S3 minus S2, because S3 is equal to S4 and S2 is equal to S1. So, we can always write S4 minus S1. So, these two will be cancelled out and we can comfortably write COP of a Carnot cycle is TL divided by TH minus TL. It is simple. So, if a Carnot, if a refrigeration cycle is a Carnot cycle working between two temperatures, if we know the higher temperature and lower temperature, we can find the COP of the system. Now, there is another device which is known as heat pump. Water pump is used for pumping the water, heat pump is used for pumping the heat. We are confining ourselves here, our concerned area of heat transfer here. Suppose I want to heat this room. I will give you an example of heat pump. Suppose I want to heat this room during winters. Outside temperature is 10 degrees centigrade. I want to maintain temperature here 25 degrees centigrade. I can use a heat pump which will work here, in this case reverse Carnot cycle. It will take heat from the surroundings at lower temperature at 10 degrees centigrade and pump heat to the room which is at 25 degrees centigrade. So, our heat transfer of concerns become this, right. In that case, the efficiency of the heat pump can be expressed as QH divided by QH minus QL. So, this is known as energy performance ratio of heat pump. Now, if you compare these two, then energy performance ratio turns out to be 1 plus COP. Suppose for an air conditioner or refrigeration cycle, the COP is 3. Energy performance ratio, if you use that cycle as a heat pump, the energy performance ratio will become 4. Now, instead of using a room heater, suppose we want to heat a high-rise building with 1000 kilowatt heater, electrical heater. The energy consumed by the heater is 1000 kilowatt. Instead of using a 1000 kilowatt heater, if you use reverse Carnot cycle for the heat transfer of 1000 kilowatt. So let's go back to the Carnot cycle again. So this TH is 1000 kilowatt, right? And EPR, energy performance ratio, is for the cycle, let us say it is 4, because COP of refrigeration cycle is normally 3. So energy performance ratio of heat pump, let us take 4. So the total energy required, that is work, it will be 1000 kilowatt divided by 4 equal to 250 kilowatt. So we will be in this case we will be saving 75% of the energy. So it is always advisable to use heat pump in place of electrical resistance heating of the room. Now in Carnot cycle there are some inherent problems for practical application, but with certain modifications this cycle can be used for practical purpose. For example, in reverse Carnot cycle it is said if you use gas, then there are certain problems because constant temperature, heat addition and heat rejection, QH and QL. So constant temperature, heat addition and heat rejection is a problem because process has to be very slow. In order to avoid this, if instead of using a gas, if we use vapor and we operate in a zone where phase change of vapor takes place, write this, because during, as we know, during boiling and condensation process the temperature remains same. So heat rejection, if heat rejection takes place during condensation of the vapor and this heat transfer rate to the fluid takes place for the boiling of the vapor, during the boiling of the vapor, we come close to the practicality of this cycle. So instead of gas, if we use vapor in place of gases in the cycle, it becomes easier for addition and rejection of heat in the cycle. So reverse Carnot cycle is an imaginary cycle which can produce the refrigerating effect. Now method of refrigeration. Now there are different methods of refrigeration. First of all, ice refrigeration. In old days there used to be cabinets. In cabinets ice was put and food stuff was put in other drawers of the cabinet, and by natural circulation of air the temperature was maintained in the cabinet. So this type of refrigeration method is known as ice refrigeration method. Dry ice refrigeration, that is very popular. Dry ice is nothing but solid carbon dioxide. So when this ice takes heat from the surrounding, the solid is sublimated into the carbon dioxide. So this type of refrigeration is very helpful in transportation of foodstuffs, because if we keep dry ice in the wagon, if we keep water ice in the wagon, after melting the water will spread on the floor, but in this case the carbon dioxide will be formed and it will be vented to the surroundings. The third one is evaporative refrigeration. Evaporative refrigeration methods are widely used in India. The cooling of water in the earthen pots is a very good example of evaporative cooling. Now expansion of air. Suppose we take air at 300 Kelvin, that is 27 degrees centigrade, and pressure is 1 bar, pressurize it to 3 bar, using the relation T2 by T1 is equal to P2 by P1 raised to power gamma minus 1 over gamma for air. It is if it is isentropically compressed to 3 bar, the temperature will become 410.75 Kelvin, right. Now, if we cool again this air to 300 Kelvin at 3 bar pressure and expand it to 1 bar, the temperature will be reduced to 219.1 Kelvin. 219.1 Kelvin is very low temperature. So, this is how we can get low temperature by expansion of air, by throttling of gases. Now, for throttling of the gases, there is a Joule-Thomson coefficient. For if we have a characteristic curve between temperature and pressure and there is a constant enthalpy lines, suppose there is a constant enthalpy line, and if we increase enthalpy, the characteristic curve will become like this. If we further increase enthalpy, the characteristic curve will become like this. So, characteristic curve is attaining a peak, right, and H1, and it is less than H2 and it is less than H3. Now, Joule-Thomson coefficient, if you look at the Joule-Thomson coefficient, this is point A. If we are expanding the gases, if we are throttling the ideal gas, there is no change in temperature. Throttling of ideal gas will not lead any change in temperature, but if it is a real gas, then if we are throttling from B to A, because in throttling the pressure will reduce, if we are throttling from B to A, temperature will rise. But if we are operating in this region, when we are throttling from A to C, the temperature will fall. So, by using the throttling of real gases, we can get the cooling effect. Now, remaining two, vapor compression refrigeration and steam jet refrigeration, there are another two methods of producing refrigeration effect. We will be discussing these two methods in details in subsequent lectures. Thank you.